So now that we understand what a basis is, it is a linearly independent spanning set for a vector space. We found out in the last activity that vector spaces can have multiple different bases. Right? So anytime you say the word basis, you should probably put the indefinite article a basis in front of it instead of saying the basis, because if you say the basis, it connotes that there's only one. But there's infinitely many for any vector space of positive dimension. But what all of the different bases for a given vector space share in common is that they all have the same number of vectors in them. Right? Any basis for any basis for R3 is going to have 3 vectors in it. Whether those 3 vectors are the friendly standard basis or whether there's some other nasty collection of 3 vectors. The important thing is that it has 3 vectors in it. And so that's what's called an invariant of dimension. The number of vectors in a basis for a vector space is always the same no matter which basis we pick for it. And so that number gets called the dimension of the vector space. So it's a property that attaches not to the basis that we choose, but to the vector space which is being described. And that's ultimately what we want to be able to do in linear algebra, is to describe vector spaces, not just to describe their bases, to describe something that doesn't depend on what basis we use. And the dimension is one of those properties. So R3 is a 3-dimensional space because no matter what basis I give you for it, that basis is going to have 3 vectors in it. Right? So the dimension of a vector space is just how many vectors are in one of its bases, no matter what basis was being chosen. So then, just to wrap things up for today, let's just do a couple of these examples with your group to find the dimension of each of the subspaces which is being described here inside of 4-dimensional space by computing in a relevant reduced row echelon form. We'll do this for about 5 or 6 minutes, and then we'll just come back and say our farewells for the day. All right, then just to wrap up this activity, to find the dimension of each of these subspaces, what you did was figure out what is the largest linearly independent set that is a subset of these vectors. Right? To figure that out, you put these vectors into the columns of a matrix that you then found the reduced row echelon form of. And you made a conclusion that, for example, in this first one that you row reduced, it had 3 pivot columns and 1 non-pivot column. So that 1 non-pivot column is telling me that this set of vectors was not linearly independent because of that free variable that would exist in its homogeneous equation. And so if we were to remove that non-pivot column and remove that non-pivot column from the original list of vectors, we would have gotten a linearly independent set that has the same span as the original set of 4 did. And so that new set is going to be a basis for that subspace that's being spanned by these vectors. And therefore, since that basis has 3 vectors in it, that must mean that the span of these 4 vectors is a 3-dimensional subspace sitting inside of R4. Similarly for the other examples. So what are we really doing? What are we really counting when we're counting the dimensions of a subspace spanned by a given set of vectors? What am I looking for? When we are counting the dimension of a span, we are counting the number of pivots, the number of bound variables, which is kind of the opposite of what we were doing when we were looking for linear dependence. When I'm looking for linear dependence, I'm counting the non-pivot columns, right, and trying to take them away. So once I take away all the non-pivot columns, then I get a basis for the space that is being spanned, because then I get a spanning set which is also linearly independent because every one of its columns has a pivot, and therefore the only solution to the homogeneous equation with those vectors is the trivial solution with all linear combination coefficients set equal to 0. So we finally know what dimension is and how to talk about it. That if I want to find a basis for a vector space, what I should do is I should just start with a big bucket of vectors that I think is enough to span the entire space, and then stick them in a matrix and row reduce them, right? And if I'm lacking a column that doesn't have a pivot, if I have a column that doesn't have a pivot, then that is a vector that in my original bucket was linearly dependent with the others, and so I should throw it away. And if I throw away all of the original vectors that had non-pivot columns in the reduced row echelon form, then what I get is a basis. And the number of those columns, which is the same as the number of pivot columns, that number is the dimension of the subspace that was spanned by my original bucket of vectors.